Hello and welcome. In this video, you will learn about density and urban form. Let's start with the concept of population density. What is it? You could say it is simply a measure of how many people share a unit of space. Or in other words, it is the ratio of people to land area. Land area can be measured as hectares, acres, square kilometers, or square miles. Let us look at the density of some cities. Maybe one of these cities is yours. This is Houston, Texas. This is generally considered a city with a low population density of about 250 people per square kilometer. What can be observed here is a high-rise central business district, and around it, quite a spread out city with low-rise buildings, lots of roads and open space. Let us look at another example, Perth, Australia. It does share some of the key features with Houston. It has only a slightly higher density, and there is again a high-rise central business district, there's open green space, and vacant lots. Then, quite a different type of city. Stockholm, Sweden, one of the old European cities. Here we do not see many roads. The roads seem to be integrated into the urban tissue. There are some smaller parks around it and open water. Generally, the buildings are not very high, 4 to 6 stories. But then, throughout the city, here we have a high population density of about 3,500 people per square kilometer. Here, yet again, a very different type of city, Hong Kong, with a population density of 6,500 people per square kilometer. Imagine you stand in between these high-rise buildings looking through these street canyons. This is how you achieve really high densities. Yet again, another example with even higher densities, the old historical center of Tokyo with more than 14,000 people per square kilometer. You see a similar pattern here. Quite a compact urban fabric, high rises, and little green or open space. One of the conclusions from these examples is that to achieve high densities, you need high-rise buildings and a compact urban fabric. Or in other words, an urban fabric with little open, unbuilt space. But there is a problem with these absolute statements about density. You can call this the boundary problem. It is the question about where does a city start and where does it end. The answer to this question will affect the value of density you arrive at, because it determines the value of the denominator when calculating the ratio of population to land area. Let us look at this problem using the example of Tokyo. Tokyo is the largest metropolitan area in the world with more than 40 million people. And, depending on which document you consult, the area of Tokyo can be up to 30,000 square kilometers, or larger than Belgium. The population density, meanwhile, does vary between 1,200 to more than 14,000 people per square kilometer. But that really depends on what you define as the city. For example, the historical center of Tokyo. Until 1943, this was defined as the city of Tokyo. In this highly populated center, we have the high population densities of more than 40,000 people per square kilometer that I mentioned. But after 1943, the historic center became part of the wider Tokyo metropolis. In this most commonly used reference area for Tokyo, density already drops to about 2,600 people per square kilometer. Why is that? One reason for this is that this area incorporates more sparsely settled rural districts, but also more parks, infrastructure such as roads and open spaces are added as you move away from the city center. And then, if you go even bigger, the national capital region that is home to 40 million people, then the density drops further to about 1,200 people per square kilometer. The reason for this are the same as before. As the definition of the city expands, more and more small villages with low population densities or even mountain areas are included, further reducing the population density. The message is, every time you hear a population density, ask yourself, where has it been measured and what is the reference area used? But there is another problem. The different population densities are difficult to spot. Look at the next slide. What do you think? Which of these two urban areas in the Netherlands has the higher population density? Bijlmer on the left or Betongdorp on the right? Easy, right? Well, they both have the same population density, but they look very different, don't they? So, population density does not reveal anything about the spatial patterns of a city. In other words, it does not inform about the urban form, which is defined as the spatial patterns of the permanent physical objects in a city, so the buildings and the infrastructure. There are two indicators that can be used to assess the urban form: the floor space index or the floor area ratio, that give an indication of the built intensity of an area, and the ground space index that expresses the compactness of the built environment of an area, the built pressure. Let's look at how these indicators are calculated. We first need to understand three key variables. Firstly, the floor area, or the sum of the space available at all stories of a building. Secondly, the plan area, or the reference area. This can be privately owned built and non-built areas associated to a building, such as the property on which a building is built, the so-called lot. But it can also be the area that includes playgrounds, car parks, or infrastructure. This is called the island or block. Or it can be a district comprising many islands, roads, major roads, water areas, and large public space. The third and last variable is the building footprint, or the area on which the building is built. From these variables, two indicators can be derived. The floor space index can take the value of between 0 and any number. It is calculated by dividing the floor area by the reference area. It answers the question of how many times the floor area can cover the plan area. The ground space index can take a maximum value of 1. It answers the question of how much built-up space there is in a plan area. So let me explain this using some Lego cubes. Imagine that this yellow cube here is a story of a house. So it's our floor area. If we add one more cube, we have twice the initial floor area. If we add another cube, we have 3 times the original floor area. And if we yet add a fourth cube, we have 4 times the original floor area. Imagine this is the footprint of our building. In other words, the area that is covered by our building. We have now both components that we need to understand the floor space index. We have the floor area and we have the plan area. If I now take the floor space and distribute the floor space across my plan area in that manner, I have a floor space index of 1. If I remove one cube and place it on top here, how has my floor area changed? Well, it has. How has my floor space index changed? Well, it has in fact not changed at all. This is still 1. If I add a cube here, it remains 1. And if I add another cube here, it remains still 1. The message is that the floor space index tells us something about the relationship between the area of floor in comparison to the area of our plan area. If I redo this and add 2 more cubes here, we have a floor area of 1.5, floor space index of 1.5. If I add more, we have a floor space index of 2. Let's look at the ground space index and what that means. Again, we have the plan area and we have in this way a floor space index of 1. We can now also say that we have a ground space index of 1. All our ground is covered. A ground space index of 1. If I move my cubes this way, my ground space index reduces to only 0.5. The maximum of the ground space index is 1, by the way. The ground space index reduces further to 0.25. 25% of the plan area are built on. This is very different from the floor space index, which remains 1 in this sort of setup, no matter how I distribute the space. But the ground space index changes every time I alter the arrangement of the cubes. How can we actually use this? You can, for instance, plot the floor space index against the ground space index, and based on this, you can say how urbanized an area is. As you can see in this picture, at low ground space and floor space index, we have rural areas. There's not much built. There's lots of open space, and the buildings are not very high. As you move up on the y-axis and sideways on the x-axis, the urban areas become much more compact and more urban. If we now put Bijlmer and Betondorp into this picture, we can see that Bijlmer is much more rural. Why is that? It has a slightly higher FSI, but it is not a very compact build. It has lots of open space, which in this classification is defined as more rural. Betondorp, on the other hand, is more urban and is more compact, and distances between buildings are short. So what can be concluded from this is that the floor space index and the ground space index are useful indicators to define the physical layout of a city, and that you should always ask what the reference area for determining densities, floor space index and ground space index was. So I challenge you to be critical about density measures and to spot the differences in urban form in your city.